In section 4.4, we will study the fundamental theorem of calculus. Given f of x is continuous on a closed interval a to b, and little f of x is the derivative with respect to x of capital F of x, or another way of saying that is capital F of x is an antiderivative of little f of x, then the integral from a to b of f of x dx is equal to capital F of x, the antiderivative, evaluated from a to b. And what this notation means you do is you evaluate f at b and then subtract evaluating f at a. Now, to help you understand why this works, let's do the integration here. Integral a to b of little f of x dx would equal capital F of x plus a constant. And then we have to evaluate that from a to b. So then that would equal capital F evaluated at b plus c, the constant of integration, minus capital F evaluated at a plus the constant of integration. And notice that we would have c minus c, those two cancel out, and that's how we end up with f of b minus f of a. And this is a really powerful tool to use because it makes finding definite integrals so much faster than what we had to do prior to this, which was to do the infinite limit of a sum to get that definite integral. So let's take a look at this example where we have the integral from 1 to 5 of x dx. So to do this part, where we get the antiderivative, capital F of x, the antiderivative of x is x squared over 2. Now remember, we would normally have a plus c, but because in the definite integral that plus c is going to cancel with the minus c, we leave it off and we are going to evaluate that from 1 to 5. So this expression right here is exactly this part of the rule. Now we have to evaluate f of b minus f of a, so that means take this antiderivative and evaluate it at 5. So we have 5 squared over 2 minus take the antiderivative and evaluate it at 1. So we would have 1 squared over 2. So we've got 25 over 2 minus 1 over 2, which is 24 over 2, which is equal to 12. So as before, a definite integral will yield a numerical answer which could be positive, negative, or 0. So applying the fundamental theorem of calculus means we take the antiderivative evaluated from a to b, that's what this part of our work was, and that turns into f at b minus f at a, which is what this part of our work was. In our next example, we have the integral from 0 to pi over 3 of secant x tangent x dx. We will be applying the fundamental theorem of calculus here. So the integral of secant x tangent x dx we know is secant x, and we will evaluate that from 0 to pi over 3. So that means the second part of the fundamental theorem, f at b minus f at a, becomes secant of pi over 3 minus secant of 0. Now, probably you think better in terms of cosine than secant, so we can switch this over to secant of pi over 3 becoming 1 over the cosine of pi over 3 minus secant of 0 would be 1 over the cosine of 0. Now we can fill in the values. This first term becomes 1 over cosine of pi over 3, which is 1/2, minus 1 over the cosine of 0, which is 1. This simplifies to be 2 minus 1, which is 1. Here, we have to do the integral from 0 to 4 of the absolute value of x minus 1 dx. Now, as soon as you see absolute value, that's your signal to write it as a piecewise defined function. We know it will be the opposite of the quantity x minus 1 if x minus 1 is negative, which happens when x is less than 1. Or it will be x minus 1 when x minus 1 is greater than or equal to 0, which is x being greater than or equal to 1. We can think of this on a number line. We know it switches over at 1, and prior to 1, it's going to be the opposite of x minus 1, or we can think of it as negative x plus 1 if we distribute that negative. And to the right of 1, it's going to be x minus 1. Now that means that this integral will have to split up into two subintervals, and the split will take place at x equals 1. So this will become the integral from 0 to 1 of, when we're to the left of 1, we have to use this form, either one of these. Let's go ahead and use the distributed form, negative x plus 1 dx, plus we will integrate from 1 to 4, and the 4 is because that is the end of our initial integral. And when we are to the right of 1, we will be integrating x minus 1 dx. Now we will apply the fundamental theorem of calculus to each of these two pieces separately. So for this first integral, we would get negative x squared over 2 plus x, and we have to evaluate that from 0 to 1, plus from this second integral, we would get x squared over 2 minus x, and we have to evaluate that from 1 to 4. Now we can do the second part of the fundamental theorem, where we do f at b minus f at a, and we have to do that on each piece separately. So working on this first one, we are going to get negative 1 squared over 2 plus 1 minus negative 0 squared over 2 plus 0. That's applying the second part of the fundamental theorem of calculus to this expression. Now we have this plus sign that we bring down. And now we have to do f at b minus f at a on this expression. So we would have 4 squared over 2 minus 4 minus 1 squared over 2 minus 1. Now we are ready to simplify. Here we see that we have negative 1/2 plus 1. That's going to be 1/2. And then here we get minus 0. Let's bring down this plus sign. From this term, we would have 16 over 2, which is 8. 8 minus 4 is 4. Then we have to subtract 1/2 minus 1, which is a negative 1/2. So now when we simplify this at the end here, we have 1/2 plus 1/2, which is 1, plus 4 is equal to 5. Next up, we will work with position function. And let's remind ourselves of the derivative relationships that we know. Acceleration is the derivative of velocity, and because velocity is the derivative of position, then that means acceleration will be the second derivative of position. Then we can also write that as integral relationships. Since acceleration is the derivative of velocity, that means velocity will be the integral of acceleration. And since velocity is the derivative of position, that means position will be the integral of velocity. Now there's a couple of terms you need to be familiar with. Displacement, which really means your distance from the starting point. It doesn't mean the total distance you've traveled. It just means at the end of my journey, how far away am I from where I started? So displacement over the interval a to b is given by this definite integral from a to b of v of t dt. And that is different than the total distance traveled during the interval a to b, which is defined to be the integral from a to b of the absolute value of velocity dt. Let's take a look at an example and see how these terms are different from each other. In this example, suppose that the velocity of an object is given by the graph below. The areas of the given regions are 20, 9, and 7. So this graph over here is a graph of the velocity function. We know this first area is above the x-axis, so then the net area is a positive 20. This second area is below the x-axis, so we know that its net area will be negative 9. And this third area is also above the x-axis, so its net area will be positive 7. First, we have to name the intervals where the object is moving to the right. Now remember that this is a graph of the velocity function. So if velocity is positive, then the object is moving to the right, and if velocity is negative, then the object is moving to the left. Now we can see that starting at 1, all the way until 5, the velocity would have positive values. So that means t in the interval from 1 to 5. And notice I have to use an open bracket on the 5 because right at 5, the velocity is 0, which means it's not positive. Union, well, here the velocity goes negative for a little while. Its values are below the x-axis. And then at 8, it's exactly 0, and then right after that becomes positive up to 10 and including 10. So we use an open bracket on the 8, and we can use a closed bracket on the 10. So on these intervals of time, our object is moving to the right. Now, we want to name the intervals where the object is moving to the left. And that will be any time the velocity is negative. And since this is a graph of the velocity, that means anytime the y values are below the x-axis. And that happens in between 5 and 8. So we can say t is between 5 and 8. And notice we had to use open brackets on both the 5 and the 8 because right at 5 and right at 8, v is equal to 0, which is neither positive nor negative. Now we have to find the displacement of the object over the interval 1 to 10. So displacement remember we just learned, is defined to be the integral from a to b of v of t dt. So that means it's going to be the integral from 1 to 10 of v of t dt. Now evaluating this definite integral is going to be pretty easy in this case because we are going to be able to use the geometry of the graph here. We will need to break this up into the integral from 1 to 5 of v of t dt plus the integral from 5 to 8 of v of t dt plus the integral from 8 to 10 of v of t dt. And using the graph, we can easily evaluate each of these integrals. This first one, because the area is 20 and it's above the x-axis, we know that net area is a positive 20 plus this second integral, its area is 9, but because it's below the x-axis, it comes in as a net area of negative 9. And then this third integral, the area under the curve is 7. It's above the x-axis, so it's positive for its net area. So that means that the object has a total displacement of 20 minus 9, which is 11, plus 7, which is 18. So this tells us that at the end of all its motion, the object is 18 units away from wherever it started. Now we want to find the total distance traveled by the object on the interval 1 to 10. Now remember, we have a definition where total distance on the interval a to b is given by the integral from a to b of the absolute value of v of t dt. So for us, our total distance is going to equal the integral from 1 to 10 of the absolute value of v of t dt. We have the graph of v of t, and what we need to do is create the graph of absolute value of v of t. We know that absolute value is a piecewise defined function where it's the opposite of v of t if v of t is less than 0, and it's v of t when v of t is greater than or equal to 0. Now on this graph, we have sections where the velocity is definitely greater than or equal to 0. And that happens on this piece here from 1 to 5. And it also happens on this piece here from 8 to 10. So for those two sections, the absolute value of v of t is just equal to v of t. But here, on the section from 5 to 8, v of t is less than 0. So that means to graph the absolute value of v of t, we have to take the opposite of v of t. And we know that that negative sign out front means to take that section of the graph and flip it over the x-axis. And now its net area will be positive 9. And so now this is a graph of absolute value of v of t. So to evaluate this integral, we can break it up into the integral from 1 to 5 of v of t dt. And the reason we can use v of t here is because since v of t is greater than or equal to 0 on that section, absolute value of v of t is just v of t. That's why we get to put that here. Plus the integral from 5 to 8. This time we have to integrate negative v of t dt, because on the part from 5 to 8, v of t is negative. Since v of t is negative, we have to take its opposite in order to get the absolute value. Then we add to that the integral from 8 to 10, and since that part of the curve is above the x-axis, we get to do v of t dt. Now it's just a matter of plugging in those values. For this first integral, we know that the net area is 20. For this second integral, we know that net area is now 9. And for this third integral, we know that net area is 7. So when we total that up, 20 plus 9 plus 7, that means the total distance traveled is 36. Now notice that the total distance traveled is a different value than the displacement here. Displacement just says, after all my traveling, how far away am I from my starting point? And in this case, it was 18 units. Whereas total distance traveled said, how much ground did I cover while I was traveling? And in this case, that's 36 units. In this example, a particle travels with a of t equals sine t, and v0 is equal to -1. First, we have to find the velocity equation. we know that velocity, v of t, is equal to the integral of a of t dt. So that means we will integrate sine of t dt, and the integral of sine t dt is going to be negative cosine t plus a constant. Now we are told that v of 0 is equal to negative 1, so we can use that by plugging into the velocity equation. Negative cosine of 0 plus c has to equal negative 1. Cosine of 0 is 1, so we have negative 1 plus c is equal to negative 1, which means c is equal to 0. So if c is 0, then that means our velocity equation, v of t, is equal to negative cosine t. Next up, we have to find the displacement of the particle over the interval 0 to pi. Displacement is defined to be the integral from a to b of v of t dt. Now we have the velocity equation, so this is going to be the integral from 0 to pi of negative cosine t dt. Remember, with a constant of negative 1, we can take that out front, so this becomes negative, and the integral of cosine t dt is equal to sine of t, and because it's a definite integral, we don't add plus c. We have to evaluate from 0 to pi. So this means that we will do negative sine of pi minus sine of 0, which is equal to negative 0 minus 0, which means our displacement is 0. So if the displacement is 0, that just means that the object ended back up at the starting place after all of its travels. Now we have to find the total distance traveled by the particle on the interval 0 to pi. Now, by definition, total distance is equal to the integral from a to b of the absolute value of v of t dt. So that means in our case, we will integrate from 0 to pi the absolute value of our velocity equation, which was negative cosine t dt. Now we can simplify because the absolute value of negative anything is the same as the absolute value of the anything. So we can say this is the integral from 0 to pi of the absolute value of cosine t dt. We know that absolute value of cosine of t is going to equal negative cosine t whenever cosine of t is negative, and we need to figure this out. And it will equal cosine of t whenever cosine of t is greater than or equal to 0. So to figure that out, let's take a look at the graph. We know the range of cosine is -1 to 1. We know our interval is from 0 to pi, so let's put pi over 2 here and pi. Cosine starts out at its maximum, goes to a root at pi over 2, and ends up at -1 at pi. So this is the graph of cosine over the interval 0 to pi. Now what we need to do is come up with the graph of the absolute value of cosine t on this interval. Well, whenever cosine of t is greater than or equal to 0, absolute value of cosine t will just be cosine t, and that's happening from 0 until pi over 2. So from 0 is less than or equal to t is less than or equal to pi over 2, absolute value of cosine t is just going to be cosine t, this part of the graph. After pi over 2 and up to pi, we see the y values of cosine are negative, and if cosine is negative, then we will have to take opposite of cosine of t. So then that means from pi over 2 is less than t is less than or equal to pi, we will have to take the opposite of cosine t, which will flip it over the x-axis. And now this is our graph of absolute value of cosine t. You can also think of this on a line graph. We know from 0 to pi over 2, the y values are positive, so we're just using cosine of t. But from pi over 2 to pi, the y values are negative, so we have to use negative cosine t. Now all this helps us decide how we can break up this integral over here, and it will become the integral from 0 to pi over 2. Remember, on that interval we're using cosine of t because cosine was already positive. So we have cosine t dt plus the integral from pi over 2 to pi. On the graph of cosine, it's negative, so from pi over 2 to pi, we have to flip it over the x-axis and use negative cosine t. Don't forget your dt there. Now we have to apply the fundamental theorem of calculus to each of these integrals separately from each other. So for this first integral, we're going to get sine of t evaluated from 0 to pi over 2. And then for this second integral, we are adding a negative, so let's subtract the sine of t evaluated from pi over 2 to pi. Simplifying, we get sine of pi over 2 minus sine of 0. That's this first simplification. Bring down this minus sign. And then here we have to evaluate sine of pi minus sine of pi over 2. This is equal to sine of pi over 2 is 1, sine of 0 is 0, then we have to subtract sine of pi, which is 0, minus sine of pi over 2, which is 1. So finally, this becomes 1 plus 1, which is 2. So once again, we notice that our total distance traveled and our displacement are two different values. The particle traveled a total distance of 2 units, even though its displacement at the end was 0, meaning it ended up back where it started from. Next, we have the mean value theorem for integrals. Let f of x be continuous on the interval a to b, then there exists c on that same interval a to b such that the integral from a to b of f of x dx is equal to the quantity b minus a times f of c. Now let's make sure we understand what this means. Take a look at this graph of f of x here. We have the same picture for both of these. Now this integral here from a to b of f of x dx would give us the area under f of x on the interval a to b. So we know that that would be shading in this area. Now let's compare that to the right-hand side, the quantity b minus a times f of c. We know that subtracting b minus a gives us the distance between a and b. So that's this distance right here. So now let's think of b minus a as the base of a rectangle, and f of c would be the height of that rectangle. And we want to choose c so that the height of the rectangle at c gives us an area that's the same as this shaded area over here. So maybe that would be somewhere in here. And now, if we make this rectangle, now the area of this rectangle is going to be the same as the area under the actual curve. So that's the concept that mean value theorem for integrals is trying to make here. So this area under f of x on a to b given by this definite integral is going to be equal to the area of the rectangle where the base is equal to b minus a and the height is equal to f of c. So in our picture that we made here, right here is the value of c. And then this height is f of c. So the area of a rectangle we know is base times height. The base is b minus a, and the height is f of c. So the concept of the mean value theorem for integrals is that we can find a value of c on that interval such that if we make a rectangle there, its area is going to exactly equal the area under the curve. In this example, f of x is equal to 4x squared on the interval 0 to 3. We have to find the value of c guaranteed by the mean value theorem for integrals. So let's remind ourselves of the concept for the mean value theorem for integrals. We know that means we will find the area under f of x on the interval a to b, and that's going to have to exactly equal the area of a rectangle on that same interval a to b. Now the area under f of x on a to b is the integral from a to b of f of x dx, and the area of the rectangle on a to b means we're taking the base, which is b minus a, the distance between a and b, and then somewhere on that interval we're picking a value of c, and then f of c will give us the height of the rectangle. So now let's fill in the specifics for this problem. We're given f of x is 4x squared on the interval 0 to 3. So that means this left-hand side will become the integral from 0 to 3 of 4x squared dx. And then the right-hand side, b minus a, is going to equal 3 minus 0. And then c, we don't know yet, so we'll just call this f of c, which if we plugged c into the function would be 4 times c squared. Now this integral we can do. We know that it would be 4 times x cubed over 3, evaluated from 0 to 3, and that will have to equal 12c squared when we simplify that right-hand side. Now when we go to evaluate this with the fundamental theorem of calculus, you can think of it as pulling that 4/3 out front, and then we can evaluate x cubed from 0 to 3. So that's how I want to think of this guy. So we would have 4/3 out front, and then we would have 3 to the third minus 0 to the third, and that has to equal 12c squared. Now on the left-hand side, the 3 in the denominator will cancel one of these 3's, so we would have 3 squared times 4, which is 36, is equal to 12c squared. Dividing both sides by 12, we now have 3 is equal to c squared. Now we have to apply the square roots property, and we get that c would be plus or minus the square root of 3. Now remember that our interval is 0 to 3, and negative radical 3 is not an element of our interval, so we reject it. Then that means we will have one value of c, and that is equal to radical 3. So what this means is if we make a rectangle whose base is between 0 and 3, so a length of 3, and then its height is f of radical 3, that area will be exactly the same as the area under f of x from 0 to 3. Now, related to the mean value theorem for integrals is a concept called average value of a function on an interval. So let me help you understand the driving force behind this. For a rectangle, area is equal to base times height. Now if we take that equation and solve it for the height, we know that means you would have area divided by base. Now if we tie this in with the mean value theorem for integrals, where the area under the curve is equal to the area of the rectangle, which remember means the integral from a to b of f of x dx is equal to b minus a, the base of the rectangle, times f of c, the height of the rectangle. So that gives us the area of the rectangle. Now if we tie it in with dividing the area by the base to get the height, then we take our area, we divide it by this base, that's this expression right here, area divided by base, and then what we would find is f of c, which is the height of the rectangle. And that height is called the average value of f on the interval a to b. So if you can remember the concept of take the area and divide it by the base of the rectangle, and what you have left is the height of the rectangle, then you have the overall concept of average value. Now let's take a look at the definition of average value. Let f of x be integrable on the interval a to b. Now remember that means the integral from a to b of f of x dx exists. Then the average value of f on that interval is given by this expression, 1 over b minus a times the integral from a to b of f of x dx. And all that is this expression where we take the area, which is integral a to b of f of x dx, and we divide by the base, which is b minus a. Now, if we look at a picture here, then here's our interval from a to b. If we integrate, that would give us the area under the curve. If we divide that area by the base, which is this length, b minus a, then what that is giving us is the average height of the function on that interval. So this y value would be the average value. Now you know when you find the average of your test scores, let's say you had 3 exams, you would add up all 3 exams and then divide by 3, and that would give you your average test value. However, when you have a function that has infinitely many values from a to b, we cannot add up infinitely many things and then divide by the number of things to get the average value. So what works is to find the area and divide by the base, because what's left over then is the average height, which is our average value. So let's try an example where we have to find the average value of f of x equals 3x squared plus 6x plus 5 on the interval 1 to 4. We know that average value is defined to be 1 over b minus a times the integral from a to b of f of x dx. So then for this problem, the average value is going to equal 1 over 4 minus 1 times the integral from 1 to 4 of 3x squared plus 6x plus 5 dx. And just a reminder that you need to have these parentheses around the entire integrand because you're integrating this whole thing with respect to x. So this is going to equal 1/3 times, we have that constant of 3 there, and then x squared integrates to x cubed over 3 plus 6 times the integral of x, which becomes x squared over 2 plus 5x. Remember, with a definite integral, we do not have plus c, but what we do have is evaluating from 1 to 4. So this is now 1/3 times the quantity x cubed plus 3x squared plus 5x that we are evaluating from 1 to 4. Let's continue to simplify. We still have that 1/3 out front. Now we have to take the 4 and plug that into the entire function we have. So we have 4 to the 3rd plus 3 times 4 squared plus 5 times 4. And then we have to subtract what we get when we plug the 1 in to the entire function again. So 1 to the 3rd plus 3 times 1 squared plus 5 times 1. We have to close this set of parentheses here, and then we have to close the bracket. Let's continue to simplify. Bring down the equal sign and the 1/3. Now 4 to the 3rd plus 3 times 4 squared plus 5 times 4 works out to be 132. Bring down this minus sign, and then over here this adds up to be 9. Bring down our equal sign. We have 1/3. Inside the brackets is going to simplify to be 123. And 1/3 of 123 is 41. So that means on average, throughout this interval, the function value is 41. The average value of the function is 41. The second fundamental theorem of calculus deals with the derivative of an integral. Given f of x is continuous on an open interval containing a, then we get these two rules. Let's look at them one at a time. First up, we have the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. Now let's look at the pieces here. The lower limit of the integration is a, which is that x value on the interval somewhere, and a is a constant. The upper limit of our integration is x, and that is our variable, and notice that it will match the variable of the derivative here. Now the t variable is what we call a dummy variable or a temporary variable. This is f of t dt, but it could be f of y dy or f of s ds. It's a temporary variable. The outcome, f of x, is in terms of the x variable, which is who we're differentiating with respect to. Now in the second case here, it's a more generalized version. We have the derivative with respect to x of the integral from a to g of x of f of t dt is equal to f of g of x g prime of x. Now let's look at the components here. A, once again, is a constant, and the upper limit of the integration is g of x, which is a function. F of t dt is using that temporary variable again. Remember, this could be f of y dy or f of k dk. Now here, when we differentiate with respect to x, we're going to get f of g of x, and then hopefully you recognize that this is just the chain rule being applied to the inside function. Now this rule over here is just a simplified version of the general rule where the upper function is just x. So if you look at this f of g of x, that becomes f of x because that upper limit is just x. And then g prime of x would just be the chain rule applied to x, which is just 1. That's why this simplifies to just be f of x. So what we're going to do right now is prove this more general rule so that you can understand why it works. So let's write a proof. And we want to find the derivative with respect to x of the integral from a to g of x of f of t dt. So we'll keep the d by dx on the outside. And then let's apply the fundamental theorem of calculus to this integral that's on the inside. We know our naming convention is that the integral of little f is capital F, or you can think of it as the derivative of capital F is little f. Then the integral of little f of t dt would be capital F of t evaluated from a to g of x. So bring down the d by dx because we have not done that yet. We have to take the upper limit of our integration and plug it into the function. So we get capital F of g of x minus, take the lower limit of the integration, plug it into the function. So we get capital F of a. Now we have the derivative with respect to x of this difference, so we can apply the derivative to each of these terms separately. So we have derivative with respect to x of capital F of g of x minus the derivative with respect to x of capital F of a. Our naming convention is that the derivative with respect to x of capital F is little f, so this turns into little f of g of x. And then because it's a composite function, we have to apply the chain rule and take it times g prime of x minus, over here we know that a is equal to a constant. Well, if we take a constant and plug it into the function, that just returns another constant, and the derivative of a constant is 0. So then this becomes f of g of x g prime of x, and we have just proven that the derivative with respect to x of the integral from a to g of x of f of t dt is equal to f of g of x, g prime of x. And this is the second fundamental theorem of calculus. So let's try some examples where we apply this rule. In this example, we have to find the derivative with respect to x of the integral from 5 to x squared of 1 over the quantity 3t plus 1 dt. Now we suspect we will be applying the second fundamental theorem of calculus because we're taking the derivative of an integral. But what we have to make sure is that our integral is set up exactly like the rule requires. So the rule says we need to have a constant as the lower limit and the function as the upper limit. 5 is a constant, that's our lower limit, and x squared is a function, is our upper limit. So we match that part, and then we need a function of another variable, f of t dt, and we do have that in here, f of t dt. Because we have this exact setup, that means we get to use the conclusion. So by the second fundamental theorem of calculus, we can get f of g of x, g prime of x. This is the rule that we are going to apply to our derivative of an integral. F refers to this inner function 1 over 3t plus 1, and we have to take g of x, which is x squared, and plug that into f. So that would become 1 over 3x squared plus 1. We just took our g of x squared and plugged it in where the t is. Now we have to take that times g prime of x. And this is where you have to be really careful. You're not finding the derivative of this. You're only finding the derivative of g, which is x squared. So that derivative is 2x. So when we write this in simplest form, we would put 2x over 3x squared plus 1. And you can see how easy it is to use the second fundamental theorem. But let me remind you, you have to make sure that you have your derivative of an integral set up in this form. In this example, we have to take the derivative with respect to x of the integral from x to 4x of cosine radical t dt. Now before we can apply the second fundamental theorem of calculus, we first have to get our integral into the proper form. The rule requires that we have a constant as the lower limit of the integral, and we can have a function as the upper limit. In our case, we have the x variable here, and we have 4x as the upper limit, but what we can do is use the properties of definite integrals, because we can think of a number line here where we have x and 4x, and we could choose a random constant, let's call it a, somewhere in between those two. Then what we can do is break this up into the derivative with respect to x of the integral from x to a of cosine radical t dt plus the integral from a to 4x cosine radical t dt. Close the big bracket. Now this second integral is set up in the way we need it to be, with the constant as the lower limit and the function as the upper limit. But this first integral is not quite set up right. The limits are backwards. But we know that we can turn this into derivative with respect to x of negative integral a to x of cosine radical t dt plus derivative with respect to x of the integral a to 4x of cosine radical t dt. Now both of these are set up exactly as we need them to be. In the case of this first one, this is the simpler rule of the second fundamental theorem of calculus, where the derivative with respect to x of the integral from a to x of f of t dt is just going to be f of x. So this first one is going to become negative cosine radical x. We bring down the plus sign, and then for this second one, we have a function up here in the top, so we know we have to apply the more generalized rule, which is going to be f of g of x, g prime of x, and that's going to become cosine of the square root of 4x times 4, because the derivative of 4x is 4. So when we simplify this, we get negative cosine radical x plus 4 cosine of 2 radical x, because we know the square root of 4 is 2.